Yes, some of the examples that I'm going to do today are in your notes, but some are not, so just check which ones are and which ones are not. The first example is with regards to tree diagrams, where we have independent events. That means that whether we have blue marbles or Smarties and green Smarties, they don't influence each other. They don't have an impact on each other. So in this example, they say we have 3 blue and 2 green Smarties, and one Smartie is taken, I'm not sure, and put back into the bucket. Determine the probability that a green and a blue Smartie is taken. Is this one on the notes? Yes. For independent events, we have a certain formula of the probability of A and B equals to the probability of A times the probability of B. This is revision of last year, so you should know this. This should not be new news. We always start a tree diagram with a dot on the left, and we do the first action. What is the first action? Take a Smartie. Okay. So you can either take a blue Smartie or you can take a green Smartie. When you draw the twigs of your tree diagram, they must be underneath each other. This is our first action. We take a Smartie. Then we have to take another Smartie. So we have a second action. They must end below each other. Should you have taken a blue one, and you take a next one, it can either be blue or green. Should you have taken a green one and you take a next one, it can either be blue or green. And then we have our outcomes. The first outcome is blue, blue. The next one is blue, green. Then we have green, blue. And green, green. The probabilities on the branch is, if we have 2 branches, it means that we have, okay, let's first count how many Smarties are there in total. 5. So S, the Smartie sample size is 5. How many blue ones out of the 5 do we have? 3. How many green ones out of the 5 do we have? 2. We place them back after we've taken it. So we still have 5 Smarties. The next branch will be, how many blue ones are there? There are still 3 out of 5. And how many green ones are there? There are still 2 out of 5. How many blue ones are there? There are still 3 out of 5. And how many green ones? There are still 2 out of 5. Now they ask, what is the probability that a green and a blue Smartie is taken? So you look at your outcomes. We are looking for green and blue. There's one, and there is one. So we have 2. Now you write the probability of a green and blue equals these probabilities multiplied. So it's 3 over 5 times 2 over 5. It's this one times this one gives you that one. And we have this one. So it's a plus. Or is plus. Or this one, 2 out of 5 times 3 out of 5. And then you get your answer, 6 over 25 plus 6 over 25. That gives you 12 over 25. So the probability, if you have 5 Smarties, where 3 is blue, 2 is green, and you need the probability of taking one color of each, the probability will be 12 over 25. Any questions? Let's move on to the next one. Okay. Now you must concentrate because they say a marble is drawn from a bag but not replaced. So once you have taken the marble, you keep it. That means that the color of that marble is decreased, the number of the colors, and the total in the bag also decreases. A second marble is drawn but not replaced. Determine the probability that both was blue and the first was red and the second was blue. So we have two sums. First, we need to draw our tree diagram. Start with a dot. The first action is we have a draw and we choose between two colors, red and blue. We have 6 red and we have 4 blue, so the sample size is 10 in the bag. So the first draw is the first 2 branches of my tree diagram. Now I have another draw, so I can draw either a red or a blue, or I can draw either a red or blue. We write our outcomes. The first one is red and red, then red and blue, then blue and red, and then blue and blue. Now for the probabilities. We start with 10 marbles. So red ones are 6 out of 10. The blue ones is 4 out of 10. Should you draw a red one, how many reds are left? 5. And how many marbles in total are left? 9. Should you draw a red one, how many blues are left? 4. And how many in total? 9. Should you have drawn a blue one, and how many reds are left? 6 out of 9. Should you have drawn a blue one, how many blues are left? 3 and the total 9. Okay. These are important. Take time to figure those probabilities out before you attempt doing the sums. Both, the probability that both was blue. Okay, let's just get the paper. Both was blue is only this one. So the probability of blue and blue equals 4 out of 10 times 3 out of 9. And that gives me 12 over 90. And you have to simplify 2 over 15. Number B. What is the probability that the first was a red one and the second was a blue one? So we look for RB. There is only one RB. That will be, the first probability is 6 over 10 times, the next probability is 4 over 9. Then we have 24 over 90, and that simplifies to 8 over 15. Okay, do you understand where we keep the marbles, then the totals change?
With the tree diagrams, why isn't the third?
Why is it not?
The third mouth thing. Because like when you see the first one, and then there's the original, the 6 and the 4, and then you take a marble out, but it's not replaced, and then there's the second one, and then when we take another one out, and then not replaced, and then there's the third one. Why isn't the third one?
Okay, but we only draw twice, not 3 times.
That is the first one, not like the original like we had before you took out.
Now, if you draw a red one, there was 6, now you draw 1. This is the start. Now you draw 1. There was 6. From the 6 red of the 10 marbles, you draw a red. So now there are 5 over 9 left. And then you draw another red. So after this draw, you would have gotten 4 out of 8 on the next branch. So you always start with what you have. And then you draw. So then we have new numbers. And then you draw. Okay. Our third example is another tree diagram. Here we have two different objects. First we have a dice, but this dice only has 4 numbers on it. And we have a coin with head and tails. So we need to draw a tree diagram of tossing the dice and the coin. First you roll the dice and then you toss the coin. Always start with a dot. If we roll the dice, how many options are there? How many branches? Nope. 4. Because our dice has 4 numbers. Oh, excuse.
But is that an even number?
Even numbers. Okay, let's start. We first roll the dice so we can get 1, 2, or 3, or 4 on the dice. Then we toss the coin. The coin has two options, tails and heads, or heads and tails. So after the dice, we have two options at each number. Heads, tails, heads, tails, heads, tails, heads, tails. And we have our outcomes. The first outcome is 1 head or 1 tail. Then you get 2 head or 2 tail. 3 head or 3 tail. 4 head or 4 tail. Before we start with the questions, we need to write our probabilities on our branches. Now, if the probability of all of them happening at once, the probability will be 1. But if you divide them in 4 options, the probabilities will also, this 1 will be divided in 4, so we get quarters. And let's do this example with decimal numbers. So this will be 1 quarter, 1 quarter, 1 quarter, 1 quarter. And that means it's 0,25, 0,25, 0,25, and 0,25. The probability of a coin is 1. But the coin has two sides. So it's half, half. Therefore, this probability will be 0,5 and all of them 0,5s. Yeah.
Why do you write it doing this?
Just to show you that you can also do tree diagrams in decimals. Okay. So this was question A, draw the tree diagram. Question B, the probability of getting a 3 and heads. And now we have to look for 3 and heads. There's 1. The probabilities are 0,25 times 0,5 and you get 0,125. You can either leave it in decimal form, or if they ask you the percentage, you can change it to the percentage. Then for number C, they ask you what's the probability of getting an even number on the dice.
No? I'll hear the question.
Pardon? Okay, coin has two options. So half of the options is heads and half of the options is tails. So the probability of getting a head is 0,5, that's a half. And the probability of getting tails is 0,5, which is also half. Alright, now they want the probability of even numbers. So we have to look for even numbers. There's one, there is one, and there is one. So we have 2h or 2t or 3h or 4t. What is ors in probability? Pluses. So we have 2h, which is 0,25 times 0,5, or 0,25 times 0,5, or 0,25 times 0,5, or 0,25 times 0,5. And that gives me, if you add everything, 0,5. If I want the percentage, 50%. Now, number D. The probability of getting a 1 or a head. So we must look for all the ones and all the heads. There is a 1, there is a 1, there is a head, there is a head, there is a head. How many are there? 1, 2, 3, 4, 5. So we write. We have 5 of the same things, 0,25 times 0,5, and that is 0,625, which is 62,5%. Right? We want the probability of a 1 or heads. So we look for all the ones and we look for all the heads. There's a 1, there's a 1. There's a head, head, head. We're not looking for 1 and head. If that was true, we only took that one. We're looking for 1 or head.
So could you have done that at the previous question as well?
Like this. Yeah. Okay.
Then what if we add and we're going to multiply?
You add if you have an or, and you multiply if you have an and. So and is multiply. Or is plus.
So then why don't we add and B? Why do we multiply?
Because we have 5 of these. This plus this plus this plus this plus this. They are all the same. So we have 5 of the same things.
So we could have had the same thing.
Yes. 5 pluses.
So then at C, why did we add? If there wasn't an add or.
You could also have said 3 times 0,25 times 0,5.
Why is it three?
What?
Why is it three? It's four.
Ag, skus, 4. Sorry. Ek het nou net daarbo gekyk. 4. Okay. Our next example. Two-way contingency tables. Is this one in your notes?
Yes.
Okay. Our first question on contingency tables is regarding boys and girls having black, brown, or blonde hair. They calculated all the children having black hair, all the children having brown hair, and all the children having blonde hair. They also calculated how many boys were there, how many girls were there, and how many children were asked in total. Our first question is, calculate the probability that the learner will have black hair. So number A, probability of black. They didn't say whether it was a boy or a girl. They just asked the probability of black hair. So you look at the total of black hair and you look at the total of children. That will be 8 over 30. Which is 4 out of 50. Always simplify. Number B, the probability of brown hair if a girl is picked. So we look at brown hair for girls, 4 out of 12. That is a third. Number C.
And let's say the 12 and the 12 are not the same, and then the 12 of the brown hair was something else. Then what did you take the 12 of the total brown instead of the 12 of the total blonde?
Because brown sort of is the main thing we're looking for. Brown hair, if it is a so we took brown of the brown stuff. Number C. Blonde hair, so the probability of blonde if a boy. Blonde for boys, 4 out of 10.
And once a lot of people it says 4 out of 18.
I think that one is wrong in the notes. Number D. The probability of a girl is blonde. Girl plus blonde hair and girls totals 6/12. That's also wrong in the notes.
Yes.
I'll go and look again at the notes. Okay, our next one is Venn diagrams. Is this one in your notes? Okay. The probability that Jack drinks a cold drink Now I'm going to show you how to get to your numbers inside your Venn diagram. The Jack drinks a cold drink is 0,6. We have cold drink and we have water. So cold drink is 0,6. I don't write it inside yet. The probability that he drinks water is 0,3. The probability that it doesn't drink anything is 0,2. So this we can write 0,2. It doesn't drink anything. Determine the probability that it drinks cold drink and water. So it's this part. And drinks only one of the two, so only that or only that. Now we need to get our numbers inside. Let's make this x. So the probability of drinking a cold drink is 0,6. Therefore, this part will be 0,6 minus x. The probability of drinking water is 0,3. So this part will be 0,3 minus x. Now they ask, determine the probability that he drinks cold drink and water. So we're looking for the value of x. When you work with decimal probabilities, our sample size is always 1. 1, 0 or 1. Number 8. The probability of drinking cold drink and water. Can you remember there was a formula that says the probability of cold drink plus the probability of water minus the probability of both equals 1. So we're going to use that one. We have the probability of cold drink or water plus the probability of not cold drink or water, and that is 1. That means the probability of all three those plus the probability of not drinking one is 1. Does that make sense? No. The probability of, let me just get, that one here. The probability of cold drink or water is this. Do you agree? He drinks cold drink or water. So the probability of those plus the probability of not drinking anything must be 1. Does that make sense? Okay, that's what I wrote here. The probability of drinking cold drink or water, the colored in one, plus the probability of not drinking cold drink or water must be 1. So now we work out the probability of cold drink or water is the probability of cold drink plus the probability of water minus the probability of cold drink and water. That's another one. Can you remember that one? Plus the probability of not cold drink or water. I'm just going to put that one to the left. Equals 1. What is the probability of drinking cold drink? 0,6. Plus the probability of drinking water? 0,3. Minus the probability of cold drink and water? X. Plus not cold drink or water? 0,2. And now you get x alone. Take the x to the left hand side. Take the 1 to the right. So it's 1 minus 0,6 plus 0,3 plus 0,2. And you get x is 0,1. Yes, please.
And 0,6 is a
Positive. Okay, cold drink and water. We start with cold drink or water plus not cold drink or water equals 1. Cold drink or water, I expanded to that. It's the whole cold drink plus the whole water minus the and. Plus not that. So I just broke it up into this part plus this part plus this part plus this part is 1. And then I put in all the probabilities. Get x alone and you get 0,1. So the probability of cold drink and water here is 0,1.
Would it not have worked if you just used the equation? PA of B equals PA plus P minus PA and this one.
That formula. Now lady asks, why didn't I use this formula?
No, the one on top.
Oh, the one on top. You could also have used that one.
The one that you did, like this one, is it a fixed formula or do you just have to figure it out?
It's a fixed one. All the inside probabilities plus the not inside equals 1. Okay, let's move on to our last example. Is this one on the notes? Yeah.
Yes, note 57.
50 grade 12 learners were asked if their school lunch consisted of a sweetie, W, a chocolate, C, or fruit, F. The probabilities of each are shown in the Venn diagram. Determine the probability that a learner selected at random will have the following. Okay, quickly copy that.
Should you do it?
Okay, can I do the first one? Right, our first question is, determine the probability that a learner selected randomly will have a sweetie and, that's the sign for and, a chocolate and a fruit. So where you wrote this, and means multiply, or means plus. The sign for and is this, and the sign for or is that. So, a sweetie and a chocolate and a fruit. Where do I look in my Venn diagram? The very, very center. That will be 0,01. And that is 1%. Should they ask the percentage? Number B. I'm looking for none of the above. Okay. That means no sweetie, no chocolate, no fruit. So I'm actually looking for the probability here. How do I get that one? You take the sum of the total of these and minus it from 1 because my sample size is 1. So this will be 1 minus 0,15 plus 0,18 plus 0,3 plus 0,08 plus 0,01 plus 0,1 plus 0,15. And we get 0,03. Should they ask the percentage, it's 3%, and we can write in 0,03 outside the circles. Number C. What is the probability that the learner will have a sweetie and a chocolate, but not a fruit? So we look at sweetie and chocolate there, but not fruit, 0,18. And it's 18%. Okay, any questions on this one? Okay, for homework. Your homework is from your textbook. If you are done writing down the homework, you can start with it.